Adopting Lean NPI will reduce the design revision spins. You'll have fewer manufacturing problems. You'll reduce your time to get from design to volume production. You'll have higher manufacturing yields and product reliability. You'll have a repeatable product manufacturing process. You'll have reduced development costs. And finally, your time to market will be reduced. First, let's look at the design to manufacture flow for a typical PCB. On completion of the PCB design, some manufacturing output is generated. The manufacturing output is checked and it's verified to ensure that all of the data that's required is included and that all of the data actually looks correct. The data is then sent to the fabricators for their process preparation, and once that's complete, then they can actually fabricate the bare boards. Also, we send data for our EMS company so that they can perform their assembly and test process preparation, and then they can actually manufacture our product for us. These activities in the PCB design to manufacture flow can be divided into three categories: product design process, new product introduction or NPI process, and manufacturing execution. But what does NPI process mean? The new product introduction or NPI process is a critical phase in the development of new products. On completion of the PCB layout, we produce our manufacturing output. Then we enter a series of stages intended to verify the integrity of our manufacturing data and to define exactly what is going to be manufactured. First of those stages is building our manufacturing product model. The manufacturing product model defines exactly what is going to be manufactured. Next stage is to run through design for manufacture validation for the bare board in fabrication and also for assembly and test. Using DFM feedback, we can implement any changes that we need to make to our design in order to make the product much more manufacturable and to comply with the rules and process constraints of our manufacturers. Assembly panel, and also running design for manufacture verification on the panel itself to ensure that we haven't introduced any manufacturing problems as a result of designing the panel. Finally, we can produce our manufacturing data output for fabrication and for assembly. All of the stages you see at the moment form the NPI process. Once all of these stages are complete, we can then hand off the manufacturing data ready for process preparation. The NPI process prepares the design output data for a streamlined handoff to the manufacturing process preparation. Also, the NPI process verifies that the design output data is suitable for new manufacturing processes and process constraints. Part of our NPI process is the handoff of our manufacturing data for fabrication and assembly and test. Let's look at some of the traditional manufacturing data that we send for fabrication. Contained within our fabrication data set are Gerber files for our silt screen, our solder mask, our copper layers and our board outline. Also included are the Exelon drill files for the plated through holes, the non-plated through holes and the vias. Also plated and non-plated slots are defined using Exelon drill files. We also include miscellaneous files such as net lists or fabrication drawings or data instruction README files. The traditional data that we send for assembly include the Gerber files of the solder paste mask layers. Also included are XY component position listings, test point data files. Sometimes we include FabMaster or GenCAD data files, and also a bill of materials. Some of the miscellaneous files that we include are the assembly drawings for the top and the bottom assemblies, and also data instruction README files. All of these data files can be replaced by using ODB++ as an integrated data format. Let's see what happens to our data during manufacture. From our PCB design, our data goes on a journey through the manufacturing process. We send fabrication data to our PCB fabricators. They manufacture our bare boards. We send separate assembly and test data to our EMS company. And then finally we have a completed product. So why not send an integrated manufacturing product model? Using ODB++ as an integrated PCB exchange format, we can introduce much more information and much more intelligence into our data, which will define exactly what is going to be manufactured. One area of product design that's often overlooked is the design for manufacture, DFM. Is the product manufacturable? Normally using prototyping and production to uncover DFM issues is time-consuming and expensive. For each step within the development of a product and the ramp up to volume, it can cost 10 times more to fix a problem than at the previous step. In a recent study conducted by Aberdeen Research, it was seen that for non-Valor DFM users, the average number of revision spins per design was 2.8. For Valor users, the number of revision spins per design dropped to 1.2. So this was an average of 57% fewer revision spins than the non-Valor DFM users. This equated to approximately $21,000 per design just in material costs alone. Users of Valor NPI DFM tools are able to very quickly identify manufacturing violations and also identify reliability and yield issues with their designs. Using a traffic lighting system of red, yellow and green, it's very quick to decide the severity level of each violation and then correct it accordingly. The red violations are real manufacturing problems that are going to stop the manufacture of the product, whereas the yellow results show areas of the design that could be modified or improved upon, which will then result in yield and reliability improvements. Current DFM within the design flow. What this means is to use the Valor NPI DFM tool at key milestone stages in the design. So for example, if we have our component placement complete, we can run an assembly DFM analysis on our design at a very early stage. This will highlight any component placement problems so that they can be corrected before the design goes too far and becomes very difficult to rework. We then move on to routing our critical nets, and at this stage we can fix those nets having run a fabrication analysis to ensure that there aren't any fabrication problems with those nets. Clearly we do not want to have to go back and rework our design and rework our critical nets at a later stage. Again, it may be very difficult if we find DFM problems. The next stage in the design, we can route the remainder of the board, creating our copper planes, and at that stage we can also run a second fabrication analysis. So we're really building up a good picture of our design, finding out where the design could be improved upon for reliability and yield, and also from the point of view of real manufacturing violations. When the design is complete, we can run a final DFM verification for fabrication, assembly, test, and also we can run a netlist comparison between the CAD netlist and the copper and interconnect netlist contained within our data. Once we've completed the DFM verification, then we can release our data for manufacture. So, running DFM on completion of design is normally too late. Catching DFM problems early during the PCB design will save a lot of time, as fixes are very much more difficult to correct at a later stage. The DFM analysis results are linked back to the CAD layout tool for resolution to make it very easy to find and modify the design to accommodate the DFM problems. Also, we find it helps PCB designers become more manufacturing aware so that they design manufacturing in mind. Implement Lean NPI. Let's look at our best practice Lean NPI process and break it down into steps. Firstly, we design our PCB using our design layout tool, and we output ODB++ data and enter the product modeling stage of the NPI process. Here we define exactly what is going to be manufactured. We then can run DFM analysis and use the DFM feedback to modify our design in order to correct any problems that we find during DFM analysis. We can then design our assembly panel and verify that the assembly panel does not have any DFM problems associated with it. Next, we can use automated methods to output our final manufacturing data for fabrication and for assembly and test. We hand off that data to the manufacturers for their process preparation stages, and they both use the enhanced ODB++ manufacturing output that we've generated. Finally, the fabrication execution and the assembly and test execution can be performed. Now we'll see a definition of Lean NPI. Lean NPI can be defined as using enhanced intelligent ODB++ product model data, using concurrent DFM during the PCB design, and using DFM rules which are derived directly from the manufacturer's rules and process constraints. Adopting all three will result in a Lean NPI process. Thank you for listening. I hope it's been informative.